Hello. We're going to be doing some more proving today. It's a little late, probably a shorter stream today, because I've had a real busy day, but we should get something done. I might try a couple of these, or I might look at the next chapter instead. But I might come back to a couple of those, see if I can tick off a few more of them. How's my, now I need to check my bitrate, as always. Now where is it? Where's my bitrate? How's my bitrate today? Oh gosh, okay, that was loud. Hello, lazy schemer. Alright, we've got an excellent bitrate. I'm pleased to inform you. Bitrate is excellent. That means we're good to go. I mean, I don't even know what it means, honestly. I should probably spend a bit of time researching that. What does having an excellent bitrate mean? Also, there will be the sounds of children laughing in the distance. I don't think that it's ghosts, but yeah, I mean, be warned, I guess. I don't remember them being in the last stream, but they're here now anyway. Yeah, so we'll come back to those. I mean, we've done quite a lot of that now, so I'm getting a bit bored. I know they'll be good to do though. So let's learn about contrapositive proof. This is a bit larger than usual. Maybe. Anyway, let's get this. Let's get that away too. And yeah, okay, great. All right. We now examine, well, this is contrapositive proof. We now examine an alternative to direct proof called contrapositive proof. Like direct proof, the technique of contrapositive proof is used to prove conditional statements of the form if P, then Q. Although it is possible to use direct proof exclusively, there are occasions where contrapositive proof is much easier. Okay? To understand how contrapositive proof works, imagine that you need to prove a proposition of the following form. If P, then Q. This is a conditional statement of form if P, then Q, or P implies Q, I guess. Our goal is to show that this conditional statement is true. Recall that in section 2.6 we observed that P implies Q is logically equivalent to not Q implies a not P. For convenience, or what is that? Complement? Complement. For convenience, we duplicate the truth table that verifies this fact. And so we do. I guess I do find this a little counterintuitive, so yeah, I guess if this is not, yeah, so if we've got, I mean, it makes sense. It's not what I want. It makes sense, so yeah, we've got kind of this reverse pattern here. I guess it makes sense because it's the complement, so we get true, false, false against these, and then true, false, false against those, and then as a result we've got does this even make sense to me? should know. Okay, so if this is... Yeah, let me kind of flip this around. Yeah, so we've got... Yeah, okay, so the order of this is like a little bit confusing. So we've got... Oh, right, actually, no, I know what I'm missing. It's the flip. There's a flip here that I missed. Yeah, so P implies Q. I think it's red implies anyway. If P then Q implies if not Q, then not P. Right, okay, that's more intuitive. Yeah, I was reading like... this is equivalent to... Oh wow, I need to like sort out my... I was reading that this is the same as... But it's not. That's not true. That's wrong. But... this is true. And that's why those are flipped around. And then if we ordered those differently, we'd end up with true, false, or actually, we'd end up with true, true, yeah, true, false, and then false, false, yeah, or whatever, you know, you get the idea. Okay. Okay, I'll be able to remember that anyway. Right. So, according to this table, statements if P then Q and if not Q then not P are different ways of expressing exactly the same thing. The expression not Q implies not P is called the contrapositive form of P imply if P then Q. Do not confuse the two words contrapositive and converse. Recall from section 2.4 that the converse of PQ is the statement QP, which is not logically equivalent to if P then Q. Okay. Since if P then Q is logically equivalent to not Q implies not P, it follows that to prove if P then Q is true, it suffices to instead prove that if not Q, then not P is true. If we were to use direct proof to show not Q, if not Q, then not P is true, we would assume that not Q is true and use this to deduce that not P is true. This, in fact, is the basic approach of the contrapositive proof, summarized as follows. And then we've got kind of a template here. So the thing that's different about this and direct proof is, yeah, we've got a different kind of early stage. We've got a different starting point and a different ending point, so we're kind of swapping those in. Geese outs. Hello. Not P is true doesn't prove P is not true. Would you like to elaborate on that? Okay. Okay, so the setup for contrapositive proof is very simple. First line of the proof is the sentence, suppose Q is not true, or something to that effect. The last line is the sentence, therefore P is not true. Between the first and last line, we use logic and definitions to transform the statement not Q into the statement not P. Kind of like direct proof. To illustrate this new technique and to contrast it with direct proof, we now prove a proposition in two ways. First with direct proof and then with contrapositive proof. Proposition. Suppose x is an element of the integers. If 7x plus 9 is even, then x is odd. Okay, let me try this out. Let me just run through this, see if I can make any headway of this. So, what's our proposition? Proposition. Suppose x is... to get this symbol in here. Suppose x is an element of the integers. If 7x plus 9 is even, then x is odd. So, if we wanted to prove this, and we want to take the contrapositive approach, we need to prove that... So we've got an if and a then, so we're starting with not Q. So let's say I contrapositive proof ours or whatever, then we say we will attempt to prove that not, let's say, if x is not odd, even, then 7x plus 9 is not even odd. So we can kind of transform this and say, I guess we can say suppose x is even. By definition of an even number, x is... we haven't got any a's, so let's say 2a. And we can kind of move forward from that and try to construct something that shows... Hello, Bubbledon, how you doing? Good to see you. You're way behind on the VODs. Oh no. Oh no, you won't know all the lore. Don't worry, I'll do a story recap. Story recap is... well... I've been, so I've proven everything. I directly proved everything, apart from all the things that I didn't prove directly. And I learned about sets, and I learned about counting, and I learned about something else, and then I learned about direct proof, and I proved a bunch of stuff, and that took like 2 streams to prove, like, to go through, like, it probably was 3 streams to go through that whole chapter and some of the exercises, and now this. And also I played some Cyberpunk. It's still in the sick arc. You know, I have a bit of a habit of watching VODs of Cyberpunk to soothe myself when I'm feeling anxious. And I did it with my own VOD the other day. Great privilege if you stream to just watch your own VODs. And I was like, damn, this is great. Quality content. Yeah, so that's story recap. Hopefully everything makes sense. You've also watched your own VODs, but it does feel a little perverse. It does. Yeah. Yeah, I sometimes watch my own YouTube videos, but it like really messes with my brain. Like when I see myself smiling on screen, I smile as well. It's like a weird empathy thing. Like I've got like my mirror neurons are like going like hog wild, trying to like, look, I'm over there, but I also need to be here. Yeah, it's kind of, it is a bit narcissistic, but hey, why not? I mean, the guy fell into the pool for a reason, right? Well, anyway, I've had a crazy day. I went to get my hair cut, and then the guy was like, could you come back in 2 hours? And I was like, okay. And I sat outside for 2 hours, and then he cut my fringe, which it needed to happen because I'm going to a wedding, not my own wedding, but it was too long. You're getting a haircut on Sunday, lovely. Are you getting anything big done, or just a little thing? We are indeed learning the contrapositive, or I'm trying to. Oh, we could be fringe sisters. You don't have a fringe right now, but you're going to, or you already have a fringe, but you're like touching it up. Okay, suppose x is even. By definition of an even number, yeah. Okay, then I need to like mess around with this a bit. So let's say, oh yeah, and I then need to, yeah, we're going to kind of end up with trying to get to, like, I mean, let's just sketch this out. We're going to try to get, yeah, we're going to try to get that this is odd. So we should end up with like 7x plus 9 is equal to 2b, and b's got to be in the integers as well. 2b plus 1, where b is in the integers. You're gonna get a wolf cut. Oh, nice. Nice. It's a very in haircut, right? The wolf cut. People are loving it. Well, that's fantastic. I'm excited for you. What do you have now, hair-wise? You think it was in like 2 years ago? Oh, wow, I'm way out of date. It's still in for me, so. Okay, so can we put this in terms of x, maybe? We can go 7x. Yeah, we can subtract 9. To get 2b minus 8. Then we got this kind of awkward 7. We could divide by 7. Oh. It's windy. Right now you have a side part and a long swoosh. Classic, one of the classics. Oh, so this would be a big change for you. Exciting. Love a haircut, love a big haircut. Okay, this looks like complete nonsense. Okay. Well, anyway, give it a go. Let's see what the actual proof says. Okay, suppose... Right, okay, so he's starting off with doing it direct proof-wise. He's got if 7x plus 9 is even, then x is odd. Direct proof. Suppose 7x plus 9 is even, thus 7x plus 9 equals 2a. Summing to a, subtracting 6x plus 9 from both sides. Oh yeah, you can just subtract from both sides. Oh yeah. Well, yeah, I guess that makes sense. Yeah, then you do that. Then you do that. It's quite windy on the sound. Maybe I should turn it down. How are we feeling about the sound bed? Is it ridiculously loud? It's still the same from last time. Is it ridiculously loud now? Okay, fine. All right, now contrapositive proof. We start off with proof contrapositive. Suppose x is not odd. That's what I did. Thus x is even. So x equals 2a. Okay, I did that for some integer a. Then 7x plus 9 equals 7. Oh right, so we substitute x in. Okay, that was some. I should have thought of that. That would have been a way better path. Right, so we substitute that in. Then we sort of play around with it and we get to the formula for an odd number. Therefore, and then we, yeah, okay, fine. Yeah, so I just missed the substituting part. Okay, interesting. RPC 2.0 says, so the other day I was doom scrolling and this came up. Wow, what a strange little dialogue box I just got hovering over that. Okay. Oh, I was like, oh, you were looking at the little bit from the end of chapter 1 of The Art of Computer Programming, or like one of the early chapters anyway. I was okay, it's intuitive, and spent 50 minutes, got frustrated, went to ChatGPT, and the answer was... I was like, how could you ask you to prove this? You need like a PhD in math to do it. Indeed, RPC2. So the exercises in... So I describe my project as like any percenting The Art of Computer Programming, because he does include like research grade problems in the exercises. In fact, that particular problem in the early editions of the book, so you see there's a rating before each of the exercises, and that one's 45M. Anything above 45 is unsolved. And it used to be 50M, and the point was, it was like, I think it was supposed to teach you, don't just think you can solve all the exercises, because some of them you won't solve them. Anyway, somebody, not due to the book, it's like a famous problem, obviously. I say obviously, it's not obvious at all, but it is a famous problem, and then somebody solved it, and so he downgraded it to 45. Yeah. Oh well, they say it's proven in Star Trek times. Yeah, well, not nice of him. RPC to you may. It's a valid point. Knuth was he was definitely having a little joke, perhaps at our expense. At least you only wasted 15 minutes on it. Some people waste their whole careers trying to solve that problem, if you can believe it. I really feel for the people who spent their whole careers on it and didn't solve it, and then the person who solved it did. And then they were like, you know, in a way, probably if you can't solve it, you're kind of hoping maybe, well, maybe you're not. Probably if you're a mathematician, you probably think, I hope somebody solves it, even if it's not me. But I would feel a bit gutted. I think. Anyway, I think the point is that Knuth is trying to get us to know is that don't think you can do all the exercises, because you can't. You're not good enough. You even if you're really, really good, you might solve like one of the unsolved problems, and that would be incredible. So he didn't even get a Fields Medal for it because he was too young. Is there an age limit, or was it just his vibe? The Fields committee was like, okay, boomer, whatever. 40 is the age limit. Wow, I did not know that. Oh, it's what the Fields Medal was invented for. Uh-huh. There you go. All right. Well, I've got about, let's say, 5 plus or minus 2 years to get really good at maths, enough to win a Fields Medal. Do we think? Do we think I can do it? Votes in the chat. I'm pretty sure I'm pretty sure I can do it. Okay, you and me can both get there. I believe in us. Yeah, we can do that. We'll win one together, Bob the Don. Okay. Alright, well I didn't do that one. But I could have done it if I was better at everything. Alright. Now, where were we? Though the proofs have equal length, you may feel that the contrapositive proof was smoother. Really? Ah, hello Coding Bar. Hello Let's Charge King as well. How you doing? How are you, Coding Bar, as well? Well, how are you all? How are all of you? How's everyone? I've had a terrible day, but I did have a good pastry. I've actually had a rough week, if I'm honest. I know that's what you just log onto Twitch, you just see people complaining about their wonderful lives. It's actually been well, no, it's been pretty terrible. But I will say at least half of the things that have troubled me this week were actually great things about my life that I've chosen, and about half of them were complete garbage that I would lose from my life if I possibly could. Yeah, hectic, not so hectic job day actually. It was, yeah. So do we think the contrapositive version is better? Was it smoother? Maybe. I guess I just know the direct proof, so it doesn't seem that different to me, but maybe it is. Well, anyway, we'll find out. Maybe I'll find that I love it. Maybe it'll be my favorite proving technique. Okay, we've got another one. Let's see if I can... Alright, so you may feel the contrapositive proof is smoother. This is because it is easier to transform information about x into information about 7x plus 9 than the other way round. I guess that's true. For our next example, consider the following proposition concerning an integer x. Suppose x is a member of the integers. If x squared minus 6x plus 5 is even, then x is odd. Okay, let's try this. Well, let's just like barrel into this. I'm not going to read on. I'm just going to see. No. Okay, so we're supposing that x is a member of the integers. And then we've got, let's say, if x squared minus 6x plus 5 is even, then x is odd. Is odd. Oh yeah. Okay, let's contrapositive it and see how far I can get. Now we can say then we're trying to transform. I guess we're supposing, maybe suppose x is not odd. Suppose it's even. Then x equals 2a, where a, or for some integer a. And then we need to prove that this thing here, is odd. We attempt to prove this thing. What am I trying to do here? Where is everything? Why is nothing working? Okay, that's weird. Oh yeah, I know why. I forgot to implement the thing I need. Okay, so we're trying to do that. Now for that, we can say, I mean, we could try substitution. Let's try that. In that case, well, let's actually write that down. Let's try substituting 2a into the, what's that called again? Is that right? That's probably right. Okay, so if we do this, this will actually become 4a squared minus 12a, because there's the 2 in there, plus 5. And we're trying to prove that this can be put in like a 2b plus 1 form. Now, can we do that? I think we can. And then we can do... perfect jargon use. Wait, what jargon did I use? What did I say? Say it, tell me so I can say it again. Sound smarter. Smarter. Substitute into the polynomial. Nice. I mean, that does sound kind of smart, doesn't it? That's like someone who doesn't know maths idea of what sounding good at maths sounds like. That's some jargon for you. I think that's right. No, wait, it's that. Yeah. 2 times 2 is 4, right? Is that right? Should I do a poll? Okay, right. Okay, alright. Thus... the polynomial is an odd number by definition of an odd number. Something equals something something. Oh yeah. 2... forget how we do this. Forget how we do this again. Yeah, and then we... oh yeah, no, I get it. Yeah, then it's 2b plus 1 I think that's it. I mean, we'll take a look at his proof. Obviously, you can read it, so you get to know whether I'm not right, wrong. That's what that is. I'm going to read it shortly. 2x plus 1 is always odd, I guess. Yes, that's right. Buranoa. Imperfect jargon use. No. I'll never be a mathematician like this. Okay, now, how did I do? A direct proof will be problematic. We will begin by assuming that such and such is even. So such and such is 2a. Then we would need to transform this into x equals 2b plus 1 for b in the integers, but it is not quite clear how that could be done. For it would involve isolating x from the quadratic expression. However, the proof becomes very simple if we use contrapositive proof. Okay, so there are, I mean, I kind of anticipated this, but there are certain kinds of things we might want to prove that are amenable to different proof techniques and not obviously amenable to others. So I don't know, maybe direct proof would be possible in this case, or maybe not. Maybe it would just be very difficult. Maybe you'd need to use some hours, I don't know. Okay. So his version is, suppose x is in the integers, such and such is even, then such and such is odd. Proof, contrapositive. Suppose x is not odd. I did that. Thus x is even. So x is 2a for some integer a. Then he substitutes in, gets the thing I did as well. Then he extracts the 2. Therefore, x, I should follow along actually so you can follow what I'm doing. Therefore, well, it's actually not sharing the highlighting at all. Something has changed. so weird. Therefore, in fact, I can just follow along with my other cursor, actually, now I think of it. Therefore, this thing, this equation, whatever, this formula is... Right, so he's put that there, fine. Where b is the integer, yeah. Okay. Okay, consequently, this thing is odd. Therefore, it's not even. Okay, so he's finished with that. I should finish with that too. Right, and so we've then said... What are we trying to prove again? Oh yeah, we don't quite... So when we write in the contrapositive proof like this, we don't quite tie it back to the original thing we were trying to the original statement. I guess that's kind of implied by contrapositive. Fine. Okay, that's alright then. I guess I could add that on if I wanted. Okay, cool. Makes sense. In summary, since x being not odd resulted in that polynomial being not even, then x, that polynomial being even means that x is odd. Thus we have proved p if p then q by proving if not q then not p. Here is another example. Okay, suppose x and y in the real numbers. If y cubed plus yx with the x's squared is less than or equal to x cubed plus x and then y squared, then y is less than x. Right, contrapositive proof. Suppose it is not true that y is less than or equal to x, so y is greater than x. Then y minus x is greater than 0. Okay, so we've got to know that one. I mean, it's kind of obvious, but not necessarily obvious to me. Multiply both sides of that formula by the positive value x squared plus y squared, which she's just come up with. By doing that, we get... Fine, we kind of get... Well, we get this. Why is my thing not working today? Oh yeah, I'm just typing, that's why. We get this out of that, and this is here. Why is nothing working? Oh, there we go. This is here. This is here. And this is here. And then we rearrange and we get not P, I suppose. Which is good for us. Therefore, YQ, yeah, fine. So it's not true that, yeah. Proving if P then Q with the contrapositive approach necessarily involves the negated statements not P, and not Q. In working with these, we may have to use the techniques for negating statements. Oh yeah! For example, De Morgan's laws discussed in section 2.10. We'll consider such an example next. Bobadon says, the expression x squared plus y squared doesn't just come from nowhere. You can factor the expressions y cubed plus yx squared and x cubed plus xy squared into it and something else. Yeah, I guess he kind of just, I guess he notices that. It didn't jump out to me, but I guess if you know that stuff, you would probably notice that stuff quicker. I think things that look like this, I'm getting a sense that things that look kind of like this, they're like, they kind of end up in another form. Okay, suppose, alright, another example. Suppose x and y are in the integers. If 5, or okay, new symbol I've not seen in a while. If 5 does not divide, I think, x by y, x times y, then 5 does not divide x and 5 does not divide y. Proof, contrapositive. Suppose it's not true that 5 does not divide x and 5 does not divide y. By De Morgan's law, it is not true. Yeah, De Morgan's law is like, yeah, it's like, it's something really obvious. Sorry, De Morgan. It's like, but I mean, it needs to be formalized anyway. It's something like, whoa, what is that noise? It's something of this type of form. I'm not sure if this is like 100%. I don't know if this is it, actually. Let me just try and think this through. P and Q negated is not P or not Q. You have to look it up, aren't I? Alright. Oh yeah, so they're about negation. Yeah, not P and Q is equal to not P or not Q. And not P or Q is equal to not P and not Q. Okay, fine. These Dutch people have put on the kettle, I think. Wait, why is all my stuff in the wrong place now? Oh my gosh. Pull the negation into the parentheses, flips around the and the or. Okay. Thanks. Right, okay, so suppose that it's not true that 5 does not divide x and 5 does not divide y. By De Morgan's law, it is not true that 5 does not divide x, or it is not true that 5 does not divide y. Therefore, 5 divides x, or 5 divides y. We consider these possibilities separately. Case 1, suppose 5 divides x, then x equals 5a for some a in the integers. For some, from this, sorry, I don't know why I may put that in. From this, we get xy is equal to 5ay, and that equals 5ay, bracketed differently, and for that, and that means 5 divides xy. Right, because we're trying to put it in some... We're trying to put it in some form, right? Okay, fine. So, like, yeah, okay. Okay, okay. Okay, okay. I'm going to need to try that out a bit myself, I think, in the exercises. The above cases show that 5 divides xy, so it's not true that 5 does not divide xy. Okay, fine. So we need to prove both. Or do we? Do we just happen to prove both? A lot going on. I'm gonna need to try this one out. Put a question mark over that. I'm gonna need to properly dig into that one. No, there's nothing special about 5 here. It holds for any integer. Yeah, yeah, makes sense. That thing again. Such a weird glitch I get, just randomly out of nowhere. Need to figure out what that's about. I pulled that beverage can out of thin air, sorry. Sorry, that was just me swapping myself out for another multiverse version of myself. Congruence of integers. Now is a good time to introduce a new definition that occurs in many branches of mathematics and will surely play a role in some of your later courses. But our main reason for introducing it is that it provides more opportunities to practice writing proofs, both direct. So it's not boring. Both direct and contrapositive. Definition 5.1. Given integers a and b and n in the natural numbers, haven't seen those in a while, we say that a and b are congruent. Well, okay, I need to pay attention. Okay, what's going on here? Given integers a, b, and n, assume all of them in the natural numbers, we say that a and b are congruent modulo n if n divides a minus b. We express this as a triple equals, or something, a congrues, whatever, maybe somebody will tell me how this is pronounced. Oh great, now that doesn't work. Ah, brilliant. One moment, please. Okay. What's this? Is congruent to. Okay, fine. Fine. We express this as A is congruent to B mod n. Okay, this is important. If A and B are not congruent modulo n, we write this as A as not congruent to B modulo n. Now, what on earth is that? What does that mean? Okay. Young Stark says, I'm watching your videos on your main channel for a minute and found out you're going through Book of Proof same time as me. Oh, you're going through it as well? Ah, so cool. Are you doing a course, or are you just hobbyizing? Helps me feel better working through all the problems knowing someone's doing the same. Yeah. I hope it's useful to you. I'm sorry for everything I get wrong and get confused about. Thanks for your kind words. Right. So, congruency. Most likely going to start a course. I graduated in engineering, but math is calling me. Oh, nice. So you're kind of getting a taste for it. It's hard work for me too sometimes. Lol, don't worry. Thanks. That means a lot, actually. Yeah, it's rough going through this stuff. It can be tricky. It can be a real ego buster. But what isn't? In these days of AI, what ego can we have left? Right, so let's say we've got I don't know, I'm just going to pick some random numbers. Well, not exactly random. Oh wait, no, he's coming up with some examples. Let me just read the book. Just stamp the ticket. Okay. 9 is congruent to 1 mod 4 because 4 divides 9 minus 1. 6 is congruent to 10 mod 4 because 4 divides 6 minus 10. 14 is not congruent to 8 mod 4 because 4 does not divide 14 minus 8. 14 minus 8 is 6, right? Yeah. 4 does not divide 6. 20 is congruent to 4 mod 8 because 8 divides 20 minus 4. 17 is congruent to minus 4 mod 3 because 3 divides 17 minus 4. Move from remainder theorem should help understand more. Getting hype for modular arithmetic. Okay, so I've seen modulo. You know what this means? This means we've got to break out some sort of clock, right? See if I can work out what on earth this is talking about. Can I draw a circle? Probably not. Right, so let's say 4, we've got... Do we put 0 in this? Maybe. 1, 2, 3... Yeah. Oh, so windy. Right, so 9 is congruent to 1 mod 4 because 4 divides 9 minus 1. So if we tried to get to the position 9 on this, we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'd end up with 9 here. And of course 1 is at that position. So does it mean that if we're kind of following like a clock, we end up at the same position? Let's try that out with something also 4y, 6 and 10. So 6 would be 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So far, yes. Seems like if we imagine this as a clock with 4 stops, congruous means congruency. Congrually, it means they kind of end up at the same position on the clock, maybe. Wow, so windy. This is really too much. Let me turn this. Let me crank this down a little bit. Okay, all right. Colloquial arithmetic. Yeah, that's true. All right, need to sort my audio. Okay, we're doing that again. We're just flicking out of existence. What could that be? I think something's getting like killed and restarted maybe, but I don't know what. That's probably what it is. Could be the webcam? Kind of odd. Alright, sorry for flickering out of existence periodically. And it breaks, you know what it breaks? It breaks the network connection. That's really odd. From 2 you can get from 2 you can get to all the numbers in that congruency class. Congruency class, interesting, just by adding multiples of 4. Right, which of course is what it means for 4 to divide their difference. Okay. Interesting, thank you. That's very useful actually. Right. In practical terms, A is congruent to B mod n means that A and B have the same remainder when divided by n. For example, we saw above that 6 is congruent to 10 mod 4, and indeed 6 and 10 both have remainder 2 when divided by 4. Also, we saw 14 is not congruent to 8 mod 4, and sure enough 14 has remainder 2 when divided by 4, while 8 has remainder 0. To see that this is true in general, note that if A and B both have the same remainder r when divided by n, then it follows that A equals kn plus r. Yeah, makes sense. And B equals... Now what is that? What is this? What's this symbol? Anyone want to tell me what this symbol is? L? Ln plus r for some k and L in the integers. It's an L that doesn't look like a 1. Okay, okay, great. Oh, good. Riggletos says dividend equals quotient times divider plus remainder. 9 mod 4 gives 1. Okay, makes sense. Thank you. In tech, it's written as... Oh, sorry, I thought it was I really thought the semicolons were intended. I was about to believe that. Okay, so ELL. Okay, fine. Right, so it's an L. Ln plus R. Okay, I'm going to have to learn to draw that, aren't I? Alright, let me try it. Let me try it out. How'd I do? That one's... Okay. Yep, fine. Then A minus B equals Kn. Right, I need to follow this closer. To see that this is true in general, note that if A and B both have the same remainder r when divided by n, it follows that A equals Kn plus r, that makes sense, and B equals Ln plus r, and it's the same r, but it might be a different K and L. Fine. Then A minus B equals Kn plus R minus Ln plus R equals N K minus L. That's just yeah, that's just simplifying it, right? Fine. But A minus B equals N K minus L means that N divides A minus B. Okay, that makes sense. Because, yeah, okay. Because this has got to be like a factor in producing A minus B. And this has got to be... Yeah, okay, fine. So A is congruent to B mod n. Conversely, this chapter's exercise 32... No, why is there so many? Asks you to show... Why is there so many? 32! Are you serious? 32 asks you to show that if A is congruent to B, mod n, then A and B have the same remainder when divided by n. I'm not even taking that in. Conversely, this chapter's exercise 32 asks you to show that if A is congruent to B mod n, then A and B have the same remainder when divided by n. Okay, makes sense. More exercises means more opportunity to learn. That's true. We conclude this section with several proofs involving congruence of integers, but you will also test your skills with other proofs in the exercises. Okay, and we've got like a bunch of different examples here. Let me just load the features of these into my brain. I don't think I'll follow them. I'll probably go back to them. Let A and B be in the integers and n in the natural numbers. If A is congruent to B mod n, then A squared is congruent to B squared mod n. Right, and we're using direct proof here. Right. Okay, so interestingly, we're not using contrapositive proof here, so maybe some of these exercises will not require us to use contrapositive proof, so I need to be alert to that. Let's pause to consider this okay, let me just try and not be lazy about this. Sorry, I've had a pretty long day. Okay, we will use a direct proof. Suppose A is congruent to B mod n. By definition of congruence of integers, this means n divides A minus B. Then by definition of divisibility, okay, so we're chaining that on, there is an integer c for which A minus B equals nc. Then multiply both sides of this equation by A plus B. Okay, so we do that. This gets us A squared minus B squared, which gets us nc multiplied by A plus B. Since c by A plus B is in the integers, the above equation tells us that n divides... Okay, fine. N divides A squared minus B squared. The thing that I slightly stumbled on there is... I wondered whether we needed to include this c, but actually we... Where does the c come from, actually? It comes from here. Okay. Yeah, so that's fine. Let's pause to consider this proposition's meaning. It says that A is congruent to B mod n, implies A squared is congruent to B squared mod n. In other words, it says that if integers A and B have the same remainder when divided by n, then A squared and B squared also have the same remainder when divided by n. It's kind of interesting. As an example of this, 6 and 10 have the same remainder when divided by 4, and their squares 36 and 100 also have the same remainder when divided by 4. It's kind of cool. The proposition promises that this will happen for all A, B, and n. In our examples, we tend to concentrate more on how to prove propositions than what the propositions mean. This is reasonable since our main goal is to learn how to prove statements, but it is helpful to sometimes also think about the meaning of what we prove. Yeah, indeed. It gets so much cooler. Aha. Proposition. Let A, B, and C be members of the integers and n be some natural number. If A is congruent to B mod n, then AC is congruent to BC. Okay. We employ direct proof. Suppose A is congruent to B mod n. By definition 5.1, it follows that n divides A minus B. Therefore, by definition of divisibility, there exists an integer k for which A minus B is equal to nk. Multiply both sides of the equation by c to get AC minus BC equals nkc. Thus, AC minus BC equals nkc, where kc is in the integers, which means n divides AC minus BC. By definition 5.1, we have AC is congruent to BC. Okay. Contrapositive proof seems to be the best approach in our next example, since it will eliminate the symbols, doesn't divide, and is not congruent to. Proposition. Suppose a and b are in the integers and n is in the natural numbers. If 12a is not congruent to 12b mod n, then n does not divide 12. Contrapositive proof. Suppose n divides 12. Then 12 equals nc for some c in the integers. Thus 12 by a minus b equals nc by a minus b. Somehow that's come out of somewhere. And that's was that came up earlier maybe? I know I've seen it. I'm just trying to load the right vocabulary into my brain. That's the congruent modulo. Congruence. That's congruence. Okay, fine. All that nonsense is about congruence. Okay, from this, yeah, fine. We get, yeah. Okay. Oof. Hello, Widberg. How you doing? Mathematical writing. He's going to lecture us. Fair enough. We need some lecturing. How long is this bit? He's giving us a lot. Oh, he is lecturing us. Wow, he's lecturing us seriously. Okay, okay, good. All right. Now, all of you who've been upset by all of my terrible, scrappy problem-solving in notation and not using notation and all that, get ready for some Schadenfreude because I'm going to get told off by Richard. Now we have begun writing proofs, it's a good time to contemplate the craft of writing. Unlike logic and mathematics where there is a clear-cut distinction between what is right or wrong, the difference between good and bad writing is sometimes a matter of opinion. Sorry, it's really not... I really didn't try to yawn there. But there are some standard guidelines that will make your writing clearer. Some are listed below. Begin each sentence with a word, not a mathematical symbol. The reason is that sentences begin with capital letters, but mathematical symbols are case sensitive. Because X and capital X can have entirely different meanings, putting such symbols at the beginning of a sentence can lead to ambiguity. Here are some examples of bad usage, marked with X, and good usage, marked with a tick. A is a subset of B. No, no, no. We don't do that. The set A is a subset of B. Nice. X is an integer, so 2x plus 5 is an integer. Because X is an integer, 2x plus 5 is an integer. Yeah. X squared minus x plus 2 equals 0 has two solutions. No, no, no. Capital X squared minus x plus 2 equals 0 has two solutions. No, no, no. And also silly. Ow. The equation x squared minus x plus 2 equals 0 has two solutions. Yeah. Okay. All right. Oblidon says, so many of my third-year students still start sentences. Wow. You invented a tongue twister there. With variables. Those fools. You should cast them into the fire. End each sentence with a period, even when the sentence ends with a mathematical symbol or expression. No, what? Really? Okay. I mean, that seems... he's the mathematician, right? He gets to decide. But to me, that looks crazy. Like, that just looks like... Wait, what does this mean? I mean, I guess you just have to know that it doesn't mean anything. Okay. Crazy. Alright, alright. Thank you, Richard, for letting me know. Mathematical statements, equations, etc. are like English phrases that happen to contain special symbols, so use normal punctuation. Okay, fine. Understood. Understood. 3. Separate mathematical symbols and expressions with words. Not doing this can cause confusion by making distinct expressions appear to merge. Compare the clarity of the following examples. Because x squared minus 1 equals 0. Yeah, okay. So this one's bad because we got this comma, right? Yeah, we need this kind of... It follows that. Fine. Unlike A union B, A intersection B equals the empty set. Unlike A union B, the set... Okay, fine. Right, so this... I mean, I can see why this would be confusing. Okay. Bludon says it does mean something. It means it's the end of the sentence. Yeah, true. That's true. I guess I would initially assume maybe it meant something to do with the equation, but it doesn't. It just doesn't. You just have to know that it doesn't. You just have to not be mystified by it, I suppose. Avoid misuse of symbols. Symbols such as equals, less than or equals, subset of, element of, etc. are not words. While it is appropriate to use them in mathematical expressions, they are out of place in other contexts. Since the two sets are equals symbol, one is a subset of the other. Okay, fine. Yeah, fine. That I don't think I would find myself doing that. Since A is odd and X is odd, yeah, okay, that I don't even know how I'd pronounce that. This one gets a bit of extra work though. Yeah, I mean this is a bit out of control, isn't it? At all times you should avoid being mystified. True. Rule 4 you will often see being abused on a board during lectures though. Avoid using unnecessary symbols. Mathematics is confusing enough without them. Don't muddy the water even more. Fair. Use the first person plural. In mathematical writing, it is common to use the words we and us rather than I, you and me. It is as if the reader and writer are having a conversation, with the writer guiding the reader through the details of the proof. Okay? Use the active voice. This is just a suggestion, but the active voice makes your writing more lively and briefer too. I agree. The value x equals 3 is obtained through division of both sides by 5. Dividing both sides by 3, we get x equals 3. Okay, fine. Good to know that that is hammock approved, because I would probably do that anyway, if I remember to do it. 8. Explain each new symbol. In writing a proof, you must explain the meaning of every new symbol you introduce. Failure to do this can lead to ambiguity, misunderstanding, and mistakes. We don't want that. For example, consider the following two possibilities for a sentence in a proof, where A and B have been introduced on a previous line. Since A divides B, it follows that B equals AC. Since A divides B, it follows that B equals AC for some integer C. Oh no! Yeah, I've been doing that a lot. If you use the first form, then the reader may momentarily scan backwards looking for where C entered into the picture, not realizing at first that it came from the definition of divides. Oh gosh, I'm getting tired. Long day. 9. Watch out for it. The pronoun it causes confusion when it is unclear what it refers to. Ah, funny joke. If there is any possibility of confusion, you should avoid it. Here is an example. Since x is a subset of y and 0 is less than the cardinality of x, we see that it is not empty. Is it x or y? Either one would make sense, but which do we mean? Compare since x is a subset of y and 0 is less than the cardinality of x, we see that y is not empty. Fine. Fine. We love rule 6. First person plural. These rules are amazing, taken good care of. They do seem pretty well thought through. Okay, since, because, as, for, and so. In proofs, it is common to use these words as conjunctions joining two statements, and meaning that one statement is true, and as a consequence, the other true. The following statements all mean that P is true or assumed to be true, and as a consequence, Q is true also. Q since P, Q. Q because P Q, Q is P. As? Sure, why not? As PQ. Oh wait, the top ones are kind of, yeah, okay, fine. Fine, okay. Yeah, the order is different. Q for P, P, so Q, okay, fine. Notice that the meaning of these constructions is different from that of if P then Q's, for they are asserting not only that P implies Q, but also that P is true. Exercise care in using them. It must be the case that P and Q are both statements and that Q really does follow from P. Fine. X is a member of the natural numbers, so integer. Yeah, that is weird. X is a member of the natural numbers, so X is a member of the integers. Okay, fine. 11. Thus, hence, therefore, consequently. These adverbs precede a statement that follows logically from the previous sentences or clauses. Be sure that a statement follows them. Therefore, 2k plus 1, therefore a. Yeah, so that first one is bad because it's not a statement actually. Therefore, a is equal to 2k plus. Okay, fine. That one is allowed. So since, because, as, for, and so were used to mean one statement is true and as a consequence the other true. Fine. And thus, hence, therefore, and consequently, we're talking about a statement that follows logically from previous sentences or clauses, but does not say anything necessarily about the truthfulness overall or whatever. 12. Clarity is the gold standard of mathematical writing. If you think breaking a rule makes your writing clearer, then break the rule. Your mathematical writing will evolve with practice. One of the best ways to develop a good mathematical writing style is to read other people's proofs. Adapt what works and avoid what doesn't. Fair enough. Yeah, makes sense. Okay. Wow. Alright. 30. There are indeed 32. Okay. Interesting. Interesting. This is the most I've agreed with Richard so far. Good. Great. I mean, I guess it kind of makes sense. Yeah, anyway, I'll try and follow those rules. It will take some time. In many senses. Okay, what am I going to do now? We've been on for an hour and a half. I'm not going to stream for ages today. I'm probably going to stream till... I might honestly stream just till 9. Which means... Let me see what I can get through. Let me power through. And see what I can do with some of these exercises. Now, you might be expecting Richard to give us the easy ones first and the hard ones later. That is not necessarily the case with Richard's exercise difficulty. Sometimes I have a hunch the hard ones come in the middle, but I wouldn't necessarily trust him. Okay, so what have we got? suppose n is a member of the integers. I should probably stop saying that. Suppose n is an integer. Oh, okay. Let me make sure I get my full stop there. If n squared is even, then n is odd. Brutos says, your setup is really cool. Anyway, I get that wisdom. Thanks. It's all custom stuff, all like pulled together with like chewing gum and string right now. I might publish it at some point, but I think I would definitely, this is definitely a situation in which I would encourage building your own tools. Yeah, I've been iterating these over the past few weeks. I'm gonna have trouble proving that one. Oh yeah. Sorry, I'm not paying attention. Okay, right. So we're trying to do this with contrapositive proofs. So we want to we want to invert. We want to negate n is even. I don't know if we say it like this, but suppose n is odd. And then we want to get to, therefore, we want to get to, therefore, n squared is odd. We want to get there somehow. Yeah, I started work on this earlier yesterday. I'm going to try and add graphs, like plotting, into this. So I want to be able to basically be able to type in a special mode like y equals x squared or something, and then have a chart show up, and I want to be able to interact with it. That's my next big project for this. And of course I tried all the libraries, and because I'm me, I'm not going to use any of them. But I've been bubbling over is what I was about to say. I've been bubbling over, thinking about the way that you do that. Apparently the way you do it is, let's say you have like, I don't know, let's say you've got like a curve like this. Let's choose an actual better curve. Let's choose this. Let's choose that. You define a square. Let's say you start off with your big square. Let's say this is your thing here, and then you work out. I think you work out actually what, like where it hits here and here. Like you work it out for like these 2 points, and then you look at the midpoint, and if you essentially draw like an imaginary line. It's kind of awkward because I've like messed this up. Let's choose a better equation. Let's say we've got a curve that looks like this or whatever. Yeah, so you work out these 2 points, and then you work out what the direct linear midpoint is, which will be here, and then you calculate it, and then you work out what it is on the actual formula, the actual function. And if this distance is above a certain threshold, then you subdivide. That's not what I want. You subdivide into like something like this, and then you perform the same thing. So you work out here, and I guess, I don't know, this part I'm a little fuzzy on. Maybe you have to work out here or something. Anyway, and you work out, okay, how far's the midpoint? It's still a little bit further, so you subdivide again, and then you kind of, you keep going down to a level of detail where it falls within the right threshold, and then you just draw a straight line. And then eventually you end up with lots of recursively detailed squares with straight lines in them, and then that's your curve. I think it's some, maybe it's called marching squares, maybe not. Anyway, I was like vaguely mulling over like that set of ideas and how I'd implement it. So maybe I'll set up a coding environment, do it on stream at some point, and probably like fail to make any progress. But I think it'll be exciting to make such a thing. I probably should stream it actually. It probably is realistically part of this project. Yeah, and then I'll have a nice graph visualizer. And if it breaks, at least I will only have myself to blame. Yeah, so I'm working on, that's my next kind of thing to add to this. And then I want it to work for 3D shapes, and then I want to be able to draw on the shapes and still rotate the shapes, and then I want to make it all cool. Bob Dylan says, you're really inspiring me to start programming streaming. You should do it. I might do something with learning, is it Godot, like in the play, or is it Godot, like it's spelled? You should try it. Do it. In fact, I'm gonna follow you now, and then I'll get notified. You decided just summer vacay, so you got the time. You should do it. Give it a go. It's terrible, but it's also great. But are you? I must admit, I think I do know that you stream, but I'm not sure if I've seen your streams unless I'm mistaken. No, I don't think I have seen your streams, but I would like to. You stream games for your friends in a Discord server. You should try it. Give it a go. It's kind of horrible streaming programming. Like it's real rough. But I would recommend it as an activity. I know that sounds a bit paradoxical, but yeah, it's good practice. Shores. Okay, I think this is probably the most I've struggled with the pronunciation of a username. So congratulations, Shorsky. Golang is great. Some people do not like it because of its simplicity, but you do. I guess you do. Yeah, Ken Thompson worked on it. That's widely known information. But that's one of the reasons I want to look into it. It's kind of interesting. I think it's quite interesting that Ken Thompson, of course, he was a big figure in early Unix and a bunch of stuff that came out of that, but also a big figure in one of the, modern cool programming languages. It's just sort of kind of interesting that he did both. Not many people manage to do both. People often, they have their kind of early career phase, and then they have their big ideas, and then their new ideas kind of lose a bit of influence. But it's kind of interesting that Ken Thompson managed to, like, kind of stay relevant is kind of a funny way to put it, but it's like pronounced Shorshi or Shorshai. Nobody pronounces my username well on streams. Well, some people do, but my username is a typo, so I can't really blame them. Okay. Let's go. Therefore, oh, I changed the color. Therefore, n equals 2a plus 1 for some integer a. Is it not just neo? Well, it really depends on what you mean by that second word. Is it eno or eno? Neo is easy to pronounce. I don't even, I mean, there is no correct pronunciation other than what I say, and I think I change it now. I go back and forth. Eno. See, when I initially had that username, which I created. How old am I? I created. Wait. No. Oh, God. Which I created roughly 25 years ago. It was Neo Eno. Can't believe I created that username 25 years ago. Oof. That's a real oof moment. And it's only getting longer. Suppose n equals 2a plus 1 for some integer a. And we want to get to... or something. Starion1 says, is there a beginner's book or something for this kind of stuff you recommend? There is not. This book I think is designed for early college level mathematics, and I think probably that it would be hard to write a book on proofs that was more beginner level than that. That sounds kind of harsh, but basically, I mean, I think the things which are difficult about this book are basically algebra and like general knowledge of mathematics. And I don't have a good book for that because also my knowledge of that is really sketchy as well. I've managed to like plod my way through it with assistance of a lot of assistance from chat, and I have like high school mathematics, which I did like let's say 20 years ago. Is that true? Maybe. I don't know when I did. Anyway, some long while ago anyway. So I think it's like work throughable with persistence. I think probably an AI would help you work through it. Like an LLM would help you work through it probably reasonably well. But I don't have any other books that I recommend, but I would kind of recommend this book. I think it definitely does the job. I haven't felt like it's like blown my mind, but I don't think that's really necessarily the job of a teaching textbook. So yeah, but if it looks like confusing, it might be because we're in the middle of it. It like if you go back through my VODs, which are all on YouTube, you can find the link below. You will see at the start of this book that I really had far less of an idea what I'm talking about. So yeah, I've learned a lot of. If I appear to know things, most of them are from this process. Babylon says, can't believe you had Neo in your username like 2 years after The Matrix came out. And if you can believe it, it's not related to The Matrix. I didn't know anything about The Matrix at that time. Okay, so we're working towards this. And we've got n is even. Fine. So we could multiply by n, right? So we could say, I mean, I don't know about that. Let's find out. Let's find out where it goes. We could let's write this down. Let's multiply by n. Now if we did that, we would end up with n squared equals... My handwriting's not so good today. Let me do that again. N squared equals... Let me just do this a little bit more verbosely. 2a plus 1, which equals 2 na. Well, that's not good, is it? Okay, let me try that again. 2 n a plus n That's not really getting us anywhere. We've not got a plus oneable thing. Now, there was an exercise a little while ago in which I gained the information that you can't always use the step of square both sides in proofs like this. I don't know if that information applies here or not. I mean, if I could do that, let's say let's try it out. If I could do that, If I could do that, would I get an answer that made sense? If I did that, and then I did 2a plus 1. Now let me just expand this because I'm going to need to work it out anyway. Let's say we did that, and then we expanded that, and we got 2a by 2a is 4a squared. Then we have 2a plus 2a, so that's 4a plus 1. And then this is also going to equal 2 extract the 2a squared plus 2a plus 1. So that would get me an answer. But I don't know if that's allowed. I guess we can ask Richard. Richard? Richard? Would you give me the answer, please? Richard? Alright. Suppose n is a member of the integers. If n squared is even, then n is even. Proof, contrapositive. Suppose n is not even, therefore odd. So n equals 2a plus 1 for some integer a, by definition of an odd number. Thus n squared equals 2a plus 1 squared. So that was the right step. So you can use that step sometimes, though not always. I don't know why. I don't know what. I mean, maybe we were asked to prove that you could. I don't know. Yeah, and then we do that. Consequently, n squared equals 2b plus 1, but b is the integer. 2a squared plus 2a. So n squared is odd. Therefore, so he adds it on then. Okay. Interesting, so I guess I'll add that on. Therefore, n squared is not even. Come on. Get that right. Bob says, correct. You are always allowed to square both sides. Just keep in mind that the new equation is implied by the first, not equivalent to it. Aha. Right. So that's like a kind of a this symbol type of thing, but we could say it in different ways. Gosh. N equals 2a plus 1 means n is the exact same as 2a plus 1, so this implies n squared is exactly the same as 2a plus 1 squared, since if you do the same thing, you'll get the same thing. Thank you, Max. Yeah, it kind of, I mean, that's kind of what I thought. Obviously I thought because I did it, but I got a little confused because there was one proof way back, I think maybe 2 weeks ago, where that was not. I think we were asked to prove something at a more granular level. We were asked to prove. Yeah, I know we were asked to prove. We were asked to prove something like. But anyway, I mean, it is useful to have that confirmed. Thank you all. We were asked to prove like if a equals b, a squared equals b, or something like that. And my answer to that was just like, well, just square both sides. There you go. But that wasn't the given answer. Woodberg, you redeemed the hello message with that little cat creature again. Good to see you. I hope you're having a nice day. This works for any function f, not just squaring, since by definition of a function, fn is uniquely defined by n. Cool. Okay, interesting. Well, I've broken I've broken through a knowledge shield there anyway. Yeah, what was that exercise actually? I'm going to look back at that. Oh yeah, it was this, I think. It wasn't as simple as I remembered. It was question 7 here. Suppose these numbers are in the integers. If a divides b, then a squared divides b squared. Which is more complicated, isn't it? It is more complicated. It's definitely not really evident just by like squaring both sides, is it? Because this is not an equality. It's not, doesn't mean equals. Yeah, I mean you can't, I mean that would be silly even if you could do that. Like imagine if I was just like a plus b, a squared plus b. But I guess it's a thing with a truth value, so I kind of put it in the same bucket as equals, but it shouldn't be in the same bucket. A equals b implies, it's from Leo, a equals b implies a squared equals b squared. The catch is that a squared equals b squared does not imply a equals b, since the function is not one-to-one. It has two different inverses. Makes sense. Makes sense. Okay, interesting. Interesting, okay. Alright. Let's do one more. Hope you're enjoying the strange car noises. Two. All right. Suppose... Am I supposed to put this proposition thing on the start of all of them? Proposition. Suppose n is an element of the integers. If such and such is odd, then n is odd. Need a better way of doing this. I'm not using tech, anyone. Nobody suggest I learn tech. I already did that. If n is a member of the integers, if n squared is odd, then n is odd. Okay. proof. So we want to use the contrapositive method, which means we need to say suppose n is not odd, therefore n is even. If I have Unicode support, I can do yeah, indeed. Yeah, that would be especially good if I'd implemented my system properly so that I could use my shortcodes. But I didn't. I was a fool. Bob Dylan says, you want to go through Knuth's book, but you don't want to use the typesetting he invented for it. I see how it is. Well, let me tell you, right? If Knuth can create his own authoring environment, so can I, okay? If you, in a way, the most Knuth-like thing you can do is to not use tech at all and create your own. To take a huge break from all of your work and construct your own system. That's therefore tech sucks and nobody should use it. No, you should definitely use it. But, yeah, building your own tools also is cool. Suppose n is not odd, therefore n. Yeah, what am I saying? Therefore n is even. By definition of an even number, we've got n equals 2a. Besides, I like the narrative of seeing the new stuff you add every time. Glad. I don't think I added anything this week, though, sadly, apart from the more glitching. I wanted to. Okay. Right, so, and then we want to get to a kind of... We want to get to, therefore... n squared is even. Yeah. Fine. Didn't I do this already? No, I didn't. I'm doing the opposite. Why not handwrite everything? Good point. I did start off doing that, and then I was like hopelessly slow. And it got to the point where I was so I didn't have the attention span for my own handwriting, and so I got really messy. So this is my compromise. I will probably alter the compromise further as I evolve my own skills / learn more about the best way to do this. Yeah, and this is going to be n squared equals which will be something. I've altered the compromise. Pray I don't alter it any further. Yeah. Okay, well, let's just square both sides, I guess. And then let's put this in some form with a 2. This seems suspiciously easy. Okay. Yeah, we don't get answers for even number problems, so we'll just have to rely on this looking right to me. Now, we were asked also to contemplate what a direct proof would look like. So if we wanted to prove this directly, we would have to start with, well, the answer to question 1, right? No. Yes. No. No, we have to start with this. We'd have to start by taking n. We'd have to start by taking n squared is equal to 2a plus 1, and then transforming it somehow into n equals 2b plus 1. Now, would we manage to do that at all? I don't even know if we would. We'd have to square root, right? We can do that on both sides. Now, if we did that, then we could get n, but then we get like... And I don't think you can do anything with that. At least if you can, it's beyond my ability to figure out. I think there are rules about what you can do with expressions like this, but yeah, plus or minus indeed, actually. And I guess, like, do we need it on the left-hand side too? Maybe. Why not? Why not? N here is a single number, right? So it's got to be plus or minus. Saladin Bokouf. Hello, I see you on YouTube. I am sometimes on YouTube as well. Good to see you. Thanks for hanging out. We don't need it on the left. Oh yeah, I guess it's kind of... Yeah, I guess that makes sense. Because it's already on the right, so... The one says, involves subtracting the 1 from both sides, so you get n squared minus 1, which equals n plus 1 by n minus 1. Oh yeah. Well, anyway, it doesn't seem very easy to prove directly. We'd need to extract like a... We'd need to know the rules of that. What are the rules of that? Okay, so you can break apart expressions, which makes sense. You can't do anything with added, maybe. Can't do anything with expressions with additions, or I guess subtractions in them within square roots. If it was just, maybe we could. We could refactor this, maybe? I mean, this isn't the exercise, but it's kind of interesting. I believe this proof I saw started with the phrase, "the contrapositive is for cowards." Somebody had something in mind. Yeah, I mean, it doesn't look like it's going anywhere, does it? So, good motivating case for using the contrapositive, I suppose. Much easier the other way around. Much easier using that approach. Maybe if I was Mega Maths, I would find a way, but it doesn't seem like a very nice way. Okay. Well, shorter stream today. I'm going to go get some dinner. And back. I'm going away. Not forever. Don't worry. We'll get through Book of Proof. Maybe not all of it. We might not need to go through all of it, but we'll get through a decent amount. And yeah, I'm going away for a few days. So I need to pack. But I'm very good at going away. So I won't need to spend that much time packing. But yeah, so I need to do that. Need to have some dinner. Whoa, okay. Wow, every time I open the Twitch page. Let's see. Are there any good websites or books that contain mathematical problems with their solutions? Well, there's this book. This book is Creative Commons, so you can look it up. It's called Book of Proof by Richard Hammack. I didn't quite look up which one it is. And it has solutions for the odd problems, which is good. So I'd recommend that one. And then I think that The Art of Computer Programming does also contain solutions as well. Thanks for the good wishes, everyone. Now, who are we gonna raid? Am I following anyone who's streaming? Maybe. Well, we could go hang out with each of the 2i pi again. That's an option. But we did raid him last time. But it's always a good time. Always good to see the ties. Nice to see someone dressing up. All smart for a stream. Yeah, let's do it. I bet there'll be some regulars there too. So let's do it. We're raiding into the 2pi. I'm going to click the button. And whoa, it looks like some pretty exciting stuff. I'm going to click the button. And yeah, enjoy the rest of your days and week. And I will see you next Thursday. And we'll have a good time doing more of these exercises and potentially even more of the last chapter of exercises as well. And maybe I'll have some new stuff on the board as well, which will be pretty fun. Alright, 10-second timer. concludes in 7 seconds. Thanks for hanging out. Have a good time. Have a good day. I need to click the button.